is going to be recorded, and then we will also share the link once the webinar is done, so that you can take a look at it afterwards. I will be your presenter. I am Aravind Seshadri. I'm with Roll to Roll Technologies. Just to give you a background, I have been with Roll to Roll for almost 6 years now. And before that, I was at Oklahoma State University. I got my PhD in mechanical and aerospace engineering, specializing in dynamics and control of roll to roll machines. So, topics such as web guiding, tension control, registration, or some of the things that I'm familiar with. As we go along in this presentation, we'll also have some polls or some questions so that we get to know a little bit more about you and what are some of the problems, and hopefully we can take advantage of that and guide the presentation along the way. Once again, we're about ready to start the webinar. And as part of that, let me just give you a quick poll. If you can answer that really quick in the next minute or so, that will help me in terms of some of the topics that will be covered today. And we can look at um, how we can tailor that to the audience. So basically, we just wanted to know a little bit more about your knowledge about web guiding. Um, there are some people who might have no knowledge about web guiding. There are some who might just know what a web guide is, how it works, or some of them are well versed in being a designer. They can design web guides or design web guides into their machines, or some of them could be even experts that are called upon whenever you have any issues with web guiding in your operation. So I'll give just a quick minute or 30 seconds to make sure that everybody had a chance to um, answer this question. Okay, seems like we have a pretty good mix of audience here. People ranging from people with no knowledge about web guiding, and also some experts in web guiding. Okay, thank you for taking that poll. That gives me a pretty good idea on how we can proceed with the presentation. Okay, so before we start web guiding, let's just look at some of the common terminologies or names that are used for web guiding. Web guiding is also referred to as steering. Some people call as tracking. Depending upon whether we are guiding the edge of the web or a feature on the web, it might be called as edge guiding, line guiding, contrast guiding. More technical term would be like lateral control or lateral registration. These are some common terms that are used in the academia when we are talking about guiding. Sometimes it's also called as CD registration. CD, where CD stands for cross machine direction registration, and then lateral alignment. And if you're from eastern part of the world in Asia, it's commonly referred to as EPC or edge position control or line position control. Essentially, all of this means the same thing. That is, guiding or a web guide is used to position the um, web at the desired cross machine direction. And it is done so that we can enable efficient transport. If the web is not guided, then we have issues with the web crashing into the machine, quality issues, waste, and things like that. So, why do we need web guiding? Well, there are mainly four reasons why we need web guiding. Uh, first and foremost is that materials are not perfect. You might have a poorly wound roll that is not wound properly, or deliberately wound roll with an oscillation on it. And when we are trying to feed it into your roll-to-roll machine, you need to guide it so that it aligns with your process. Some materials may have thickness variation. This could be like gauge band variation, either during coating or forming processes, especially with paper mills. Different gauge papers may track differently or slide differently. Splices, whenever you have change from one roll to another, when you are joining two rolls of web, it might be a step change, or it might also be like an angular misalignment of the splice. And then some materials have a natural curvature to them, which is called as camber. So the material properties, when the materials are not perfect, that's going to have the web mistrack in your machine. It could also be due to machine itself. So either you have machines with out of round rollers, like a crown or a concave or a convex roller. Whenever you have a variation in the diameter of the roller, that's a problem. Or the rollers are not aligned properly with respect to each other. That could also cause the webs to mistrack. You might also have tension control issues. If you don't have enough tension, you don't have traction, then that's going to be an issue. And whenever you have acceleration or deceleration, that might also cause the web to mistrack. It could also be due to processes. For example, if you have a coding process and you have uneven coding across the width of the web, that's going to cause issues with tracking. And also some processes where you could have air entrained between the web and the roller, that would cause the web to lose traction and mistrack. So that could also be an issue, and that's why we need web guiding. Finally, operators, mainly when they are splicing the web or when they are putting a new parent roll into their roll-to-roll machine, they may not center it, or they may not put it at the right location. That might also cause an issue, and that might need web guiding. So web guides are necessary at different locations of the machine, because you might need alignment at different parts of the machine. That's the main thing with web guiding, is you have to put a web guide in front of any process that requires web alignment. Just to give you an example, let's say you are laminating something, and you have two uh, layers of web coming in to this lamination process. At this point, you would need a web guide so that you can align this layer and this layer with respect to each other. The guides that are used within the machine are called as intermediate guides, or they are intermediate to the machine, and the guides that are used at the entry and exit of the machines are called as terminal guides. So we're going to look at all of these in detail, but that gives you an idea of why we need web guides and where we need web guides. In terms of the location, as I mentioned, um, when you have a web guide that um, um, that is located at the entry and exit of the machine, they are called as terminal web guides. There are lots of names for these, and some of the common names are shifting stand, a shifting base, a shifting side lay, or roll positioning stands. If you're in the metals industry, it might be uncoil or recoil, and in other industries, it might be called payoff and tension reel. And specifically in these presentations and in our terminologies, we call them as unwind and rewind guide. An unwind guide is something that is at the entry of your roll-to-roll machine, while a rewind guide is at the winder or the exit of a roll-to-roll machine. So these are some of the terms that are used for terminal guides. And in terms of intermediate guides, these are the web guides that are used within the process, within the machine. There are certainly multiple types of these web guides. And the most common one is what is called as an offset pivot guide. Other names for offset pivot guides are displacement guides, positive displacement guide, pivot frame, or a table guide. The second most commonly used intermediate web guide is a remotely pivoted guide. That's a technical term, but most commonly it's called as steering guide or a steering roller or a swivel roller. Um, and then there are other less common web guides like end pivoted guide or center pivoted guide, and then even turn bars are all available. We'll take a little bit deeper look at all of these different kinds as we go along in this presentation. But most of these web guides work on a basic fundamental principle, and that is what we call it as normal entry. So um, what does normal entry say? Normal entry is basically is a web approaching a roller will always align itself perpendicular to the axis of rotation of the roller. As you see in this video right here, let me restart that. As soon as the roller on the left has a misalignment, the web started to track and it started to move in such a way that it will approach the roller on the left perpendicular to the axis of the rotation. This is the fundamental principle that is used in most of the intermediate web guides that we are going to see. And what's happening here is that the web is essentially behaving like a beam, and the angular displacement on this left hand side is bending the beam, and it's causing the beam to bend, and that's what is causing the web to track to this side. There are lots of dynamics involved in this process. How fast the web moves, how much does it move? All of those depends upon the transport conditions, the what type of web it is, what kind of traction you have, and things like that. And obviously, the static behavior is that at steady state, once this angle is set, how much is it going to move? Are we going to see any movement on this side? As you can notice that when this web moved, the upstream roller, the web was still there. It was maintaining there because it was able to have enough traction so that the lateral forces or the moment that is acting there was not able to make the web move. And whenever we have a motion like this, um, bending occurs. Bending in turn means that there are stresses developed in the web. So you're going to have a tight side and a slack side, and there's going to be a tension profile here. So these are important to understand for us in order to have a successful web guiding application or execution of a web guide. So in terms of a basic web guiding system, we are mainly dealing with four main items. Apart from the web, we're mainly dealing with four main items. One is the guide structure or the mechanism. This is the device that is actually making contact with the web, and that's the one that is need to be moved or it moves the web. Um, and there are different types of guide structures that we will go through. The other component of a web guiding system is an actuator. So actuator is something that takes an electrical signal and then it converts that into physical motion so that it moves the guide structure so that the web can be located at the desired location. The third and one of the most important components of a web guiding system is a sensor. The sensor is the device that provides the feedback. The sensor is the one that tells us where the web is. Uh, uh, where means it's inferring the position. And then finally, that signal is sent to a controller. And the controller is mainly the intelligence or the brains um, that takes that sensor signal and computes the corrective action that is required so that the actuator can move the guide mechanism to the location where we can get the desired web position. Again, another schematic of how the components of the web guides are. So web is a part of the web guiding system. And then you have the mechanism. There's an actuator inside the mechanism. The sensor gets the position feedback of where the web is, sends that information to the controller. Controller then computes an error and it sends the command to the actuator so that the mechanism can be moved to position the web at the right location. So this is a closed loop feedback control system that is a main part of a web guiding system. So let's dive into detail about different components of the web guide. First, we'll start off with guide structures and look at how guide structures are with different types of web guides that we saw. So first and foremost, we have the unwind web guide structure. In this case, you have a parent role, and that is feeding the web into your machine. And this role is on a shifting stand or a base that is supported by typically linear bearings. And then there's an actuator there that connects the moving stand with the fixed base. And then there's a sensor here that is looking at the position of the web. So the main objective of an unwind web guide is to ensure that the web that is fed into the process is at the desired location. And because of that, you have a fixed sensor that is fixed to a machine frame. And then this stand actually moves in and out of the monitor that we have here. It's going to go in and out. And the feedback from the sensor is used to make this unwind guide move in and out so that it can position at the right location. One thing I wanted to point out is that there is a shifting idler. When I say shifting idler, it means that this idler is attached to this moving base. The main reason why we do that is that if we put a sensor right here, it is not an ideal location just because of the fact that when the diameter of this roller changes, you're going to have the web plane go in and out. And if that happens, that's going to affect your guiding. So typically you would see a shifting idler. It doesn't have to be one, it can be multiple. It could also be a whole frame with a lot of rollers here. All that we need to do is that we need to put the sensor just downstream of the last shifting idler, and then the sensor is fixed to the machine frame so that we can guide the web. So those are the main things with an unwind guide. Now, when we look at rewind guide, rewind, even though we call it as a guiding, it's not actually guiding the web, it's actually chasing the web. So the main thing that is unique about this is that in a rewind system, you have a sensor that is attached to the rewind frame. All of the things in terms of the carriage, it's exactly the same. You have a sensor that is attached to the rewind stand so that when the rewind moves, the sensor also moves. And then you have a fixed idler right after this moving sensor. Like I mentioned, rewind is not really guiding the web, it's actually chasing the web. And the main reason why we do that is that we need to maintain the relative position of the web and the rewind roll. And if we put the sensor on a fixed frame and look at this rewind roll, then we would not know the relative position between those two. That's the main reason why we attach the sensor onto the moving rewind stand, so that the sensor gives us indirectly the position of the rewind stand, and the objective is to make sure that we move the rewind stand so that the middle of the sensor or the guide point of the sensor matches to the location of the web. Again, like I mentioned, it's not really guiding the web. We are chasing the web so that the rewind roll would be at the right location to get the web wound properly. So just to summarize about these two terminal guides, we can look at what are the things that we need to have a good rewind or unwind guiding system. First of all, in terms of design, we need to make sure that the mechanical structure and rigidity and stiffness are designed properly. We are moving a big mass, and depending upon the type of web, maybe metals, it may be thousands of pounds, multiple thousands of pounds that we are trying to move. And we need to make sure that the structure is rigid enough so that we can avoid any mechanical resonance. So the natural frequency of the structure should be at least 3 to 4 times the operating frequency of the control system. The other thing we need to consider, especially with these kind of guides, is that we need to size the actuator properly. When we talk about sizing the actuator, what we are talking about is it should have enough thrust so that it can push the mass, it has enough thrust to overcome the static friction, and it also has enough thrust to provide the desired acceleration to reject the disturbances or errors that may be there. Just like the mechanical structure rigidity, we need to also make sure that the actuator coupling and the actuator stiffness are all accounted for. Any play in the actuator coupling is going to reduce the stiffness of the overall system. That's going to destabilize your system. In terms of installation consideration, the main thing that we want to look for in these type of guides is the location of the sensor with respect to the moving stand. Either it's fixed to the machine frame or it's moving with the machine, with the carriage. That's the main thing. These web guides are simple. That's one of the advantages of these web guides. And these web guides really do not uh, have to take advantage of the normal entry rule, because all the rollers there are parallel to each other, so there's not going to be any misalignment in them. So there's going to be less amount of stresses on the web. The disadvantages with these kind of web guides, well, first of all, you need a high thrust actuator, especially when you have larger mass to move, and it's not cost effective if you really want good performance from a web guide. If you want to reject a high frequency disturbance, then this might not be a good choice for us. Now, moving over to intermediate web guides, we have a displacement web guide. This is another type of one of the most commonly used web guide that you're going to see, and we would recommend this as the first choice for any web guiding application. One of the main reasons for that is it actually displaces the web, and in this web guide, it's not bending the web. The reason why it's not bending the web is you have this entry span, and you have a 90-degree wrap, and then you have the plane of the carriage right here. When this carriage pivots, the pivot point is shown here, but that's a mistake. It should have been right at the edge of right here. So when this carriage rotates, pivots about the pivot point, which is at this point right there, these two rollers are actually moving in tandem. So there's no bending in this region. And then in these spans, since they are perpendicular, that motion is a pure twist. So really, there's no bending in this kind of a web guide. And if the web guide is designed properly, then these web guides can have 1-to-1 ratio, in the sense that if you move the web guide 1 unit, then the web will actually move 1 unit. So that's why we call them as a perfect web guide. And I do see a question here that says that, would you agree that an offset pivot guide acts on a different principle other than normal entry? That is correct. Just like I explained, because these two rollers are parallel to each other, there is no bending in the span. And since these two entry and the exit rollers are perpendicular, or the wrap angle are perpendicular, this span is perpendicular to the plane of motion of the waveguide, they are going to be in twist. So there's no bending, and when there's no bending, there's no normal entry coming into picture there. So like I mentioned, the twist is an important design part, and this would be our first choice for us in terms of applying it in any web guiding situation. So in terms of installation, again, we want to make sure that we have a 90-degree wrap at the entry and exit of the roller. And then there are some considerations on what is the span length at the entry and exit. So usually you can get away with half a web width. Usually we recommend about 1 to 2 web widths if possible. And if you have a stiffer web like metals, you might need a much longer um, entry and exit span. We want to locate the sensor as close as possible. This is true for any web guide. It doesn't matter if it's a displacement guide, unwind guide, rewind guide, any web guide. We want to have the sensor as close as possible in the span where the guiding action takes place. And then in this case, the recommendation is to be within the first half of the exit span. And then how long this span really depends upon how much correction you're looking for. Um, Typically, these carriages are allowed to pivot only about 5 to 10 degrees. So if you want larger correction, then you can make these spans longer. The main thing is that you need to make sure that the plane of motion of the carriage is perpendicular to the entry and exit span so that you can create a pure twist on these spans. And then as long as these rollers are moving in tandem or parallel to each other, then we will have the desired effect. They don't have to be on the same carriage. They can be on different carriages as long as we are able to have them parallel to each other. You can even have a process here. You don't really have to have just 2 rollers. You can have multiple rollers. So it provides a lot of flexibility here. And the guiding action is actually happening in the exit span. So what not to do? So we don't want to install the sensor too far away, or we don't want to install the sensor in the next span. This is mainly for control system purposes and stability. So when the waveguide makes a corrective action, that action is not seen at the sensor immediately. So if you're running really fast, you might get away with moving these sensors a little farther down. But if you're running slow, whenever this waveguide moves here, you would see that motion if the sensor is as close to the to the exit roller as possible. If you install it here or here, especially when the web stops and there is a small error, the waveguide would keep moving and that might cause the web to break or have unintended consequences. So we don't really want to have the sensor further away or in the next span. And we don't also want to have a scenario where you have an angle that is not 90 degrees. So as I mentioned, if you have a 90-degree wrap, you have twist. As soon as you introduce something which is um, deviating more from the 90-degree, you start creating bending in the web. So these kind of bending is going to act as understeering the web. It's going to cause bending that's going to understeer the web. And it also causes distortions and guide instability. So we don't really want to have any of these conditions. On the contrary, if you have a span, exit span that is spread out like this, this is going to oversteer the web. Again, it's the bending effect that is causing that, and we really don't want to do that. So ideal scenario would be to have a 90-degree wrap in and out. But there are other options for wrapping the web there. You don't have to have it just like this, what like how we showed, it's an inverted U configuration. You can have the web go in like this or like this, like a Z configuration, depending upon the space and all those things. And obviously, you can rotate all of these 90 degrees upside down, just rotate all of them. So you would have about 16 different configurations that you can do with these web guides. Uh, all in all, need to make sure that the entry and exit span are perpendicular to the plane of motion of the waveguide. All of these conditions satisfy that. Have the sensor as close to the waveguide as possible. We can satisfy that, and then you can have multiple configurations for these. So in summary, the displacement guide, the main design consideration when somebody is asked to design a waveguide, displacement guide is what is the desired correction. That kind of determines our span length for the guide span. Other than that, in terms of installation, it really depends upon how much space you have. So you can design the entry and the exit span. And then if you have a stiffer web, you might have to exaggerate that entry and exit span, make sure that we have 90-degree wrap, and then wrap the web guide based on the path. So one of the other paths would be in the same direction the web came in, and things like that. Advantages, these are simple to install. The proper installation imparts the least amount of stress on the web, and then it's pretty versatile. I put a disadvantage there, but it's really not a disadvantage. But I do want to have that here. It's like the maximum correction that you can get is designed in. So in another type of web guide where we can take advantage of steering or bending, we can get more than what the guide moves. So um, the second choice for us would be a steering guide, and in terms of how it works, it's a little bit different. You got a single roller. This is the top view, and this is kind of the side view. And this roller is installed on two raceways. They are at an angle, so the web guide actually forms an arc like that. So it moves and forms an arc back and forth. Um, that's the um, that's how we are changing the axis of rotation. And in this web guide, we are creating a bending. So there's a bending action here. It's displacing as well as bending. Um, and then in terms of the entry and the exit span, there are some guidelines for that as well, and we'll go through that. This is not an ideal choice for us, or this is not our first choice, because as I said, it's bending, so it's introducing stress. If it's not installed properly, it can cause wrinkles, creasing, web tear, and edge quality, edge stresses, and things like that. Um, so I just wanted to stop quickly and answer a couple of questions. How do we determine the minimum entry and exit span? That really depends upon your stiffness of the web and things like that, the average stress. There is a guidelines for that I can share later on. But it really depends upon the tension, the Young's modulus of the web, and then the width of the web, and then the span length. So there is a formula where we can get the minimum uh, entry and exit span lengths. And the entry and exit span need not be the same length. They can have different lengths. Also, how do you determine the correct length of the displacement guide table? Oh, the guide table length is basically based on how much correction that you need. Like I mentioned, usually the tables are made to rotate about 5 to 15 degrees. So, so the displacement that you need would be, let's say, L is the length of the span on the guide table, and theta would be the angle of displacement. The correction would be L sine theta. So that is the maximum correction you can get. So based on what maximum correction you need, you can get the length of uh, the guide, the guide span on a displacement guide. And theta is the upper limit, we can say 15 degrees. So, okay, switching back to the steering guide, in terms of installation, what do we need to look for? Well, we need to make sure that the exit span is perpendicular to the plane of motion of the waveguide. So again, the main thing that we are trying to do with this is to make sure that the exit span is in pure twist. This is where uh, uh, this allows us to have the least amount of stress in the web, so we want to do that. Now the entry and the exit span, length of that is also depending upon the stiffness of the web. You typically need a longer entry span for a rewind guide, because the motion of the web guide, or the displacement of the web, happens because of bending. So you have to follow um, those guidelines, in terms of, if you have a stiffer web, you need to have a longer span so that you can allow the bending to happen. But normally it's about 1 to 5 times the width of the web, and then the exit span can be half a web width. And there's also minimum formula for finding out the minimum um, span length there. In terms of other things here, let me go back here and talk a little bit about the instance sender. Like I mentioned, there's a raceway, two raceways here, and they are angled so that you can have the web guide go around an arc. And the center of the arc is called the instance center. This is important. We need to make sure that the instance center is within the span, and it's at a certain distance, about half the length of the span, or up to 2/3 the length of the span. Again, these are all numbers coming from the dynamic model of the web guide, and the dynamics of the web itself. And if you don't follow those conditions, then you can have a web guide oversteering, understeering, creating an awful lot of stresses, maybe wrinkles, slack edges, tight edges, and all those kind of things. So, but the main things that we want to look for is this angle. Make sure that it's 90 degrees, and then you have an entry span that is pretty long. You can have different wrap here. We don't want to go more than 45 degrees on either side. That is fine. When you do that, what you're doing is you're adding twisting per se. So whenever it goes away from this 90 degrees, it's not pure bending. There is bending and twisting that is involved there. And then we want to have an angle here, because again, when you put bending stresses here, you have the possibility of that what we call as moment transfer occur here. So the motion of this roller can actually move the web upstream of the guide roller. So in order to avoid that, we want to have certain conditions here. And then we also want the span shorter so that it becomes harder for that moment transfer to occur. So those are some of the guidelines for installation of a steering guide, and again, sensor as close as possible. Now, what not to do? Same thing. We don't want to put the sensor too far away. Um, One of the things that is not really evident is that we don't want to put the plane of motion of the web guide at anything other than 90 degrees. It's not this angle between the entry and the exit span that needs to be 90 degrees. It's actually the angle of the plane of motion of the web guide and the exit roller. That's what determines whether you're going to have a twisting action that's going to happen here or not. So when you have something like that, you're going to introduce bending in the span, and when you start bending a short span, it's not a good sign. So we don't really want to do that. So that's the main reason why we need to have the plane of motion perpendicular, not really the entry and the exit span, but the plane of motion. And then, like I mentioned, if you have the entry span and the pre-entry span longer than the entry span, then you could have moment transfer happening. That's something that you don't want to do either. In terms of wrap angles, pretty simple. You can have something going up like that or going down like that. As long as we follow this condition, that exit span is perpendicular to the plane of motion, then we are in good shape. Just to summarize the design consideration, um, design correction is one of the main things there. And the raceways that we have on the steering guides, we don't want to angle them more than 25 degrees. Um, so anywhere between like 5 to 20 degrees would be the ideal one. In terms of installation, steering guide is a lot more complicated to install. You have to consider the stiffness of the web that determines the entry span length, um, and then you also need to make sure that you're not putting too much bending stress on the web based on how stiff your web is, and then the location of the instance center, which depends upon the raceway angles. Again, that depends upon the length of the entry span. So there are lots of things going on here that we need to consider for proper installation of a steering guide. And that's one of the reasons why these web guides are prone to have a lot of issues because they're not properly installed. In terms of advantages, they're simple, so they're cost effective. It's just a single roller, so it's inexpensive, but it comes with other things that increase the overall cost of ownership. It's hard to install. A lot of attention to detail is required, and a lot of these have, especially because of the bending and things like that, loss of traction or anything like a moment transfer occurring can actually amplify the error. So a poorly installed or poorly designed steering guide can actually produce error, more amplify the error than than what it's intended to do. There are a few other types of web guides that are not used commonly, but they are center pivoted guide. Again, they are going to use the normal entry rule to try to um, steer or guide the web. So there's bending that's going to happen. So we're going to have similar considerations in terms of entry span, pre-entry span, and exiting span. Um, because they don't have any displacement, like in a steering guide, you displace and change the angle of rotation. In these guides, it's only the angle of rotation. They are usually really slow in terms of response. They're not an ideal choice in modern guiding principles, but the same design considerations have to be followed with as in a steering guide. So that kind of gives us a quick summary about different web guides and how to install them and things like that. So the next part of web guiding is the actuators. So in terms of actuators, there are lots of terminology that is involved. Some of them are thrust or power, how fast the accelerator is, what is the correction speed, what is the acceleration, stroke length, mounting, what type of coupling that we have, and things like that. Um, Actuators are pretty common or pretty standard right now. It's not as important as installation of a web guide or the sensor, but it is an important part of a web guiding system. The older actuators were either pneumatic or hydraulic. You had a hydraulic pump pumping a double acting cylinder and moving the web guide structure. These were more common in the 50s and up to about maybe 90s, before the electromechanical actuators started coming into the market. So you could have pneumatic actuators or hydraulic actuators. The hydraulic actuators have the advantage that it can provide pretty high thrust and can shift large loads pretty quickly. Even now in metals industry, hydraulic actuators are pretty common. You can see them. But the problems are that it's a problem with maintenance. You need to balance the valves and stuff like that, change the filters. They could cause leak, and this could contaminate your product. And then the precision and accuracy that you can get with an electronic actuator or electric actuator is not something that you can expect in a hydraulic actuator. So most web guides nowadays are going to use electromechanical actuators like what I have shown here. These actuators usually have a motor that drives a belt pulley kind of a system, and there's usually a lead screw, a ball screw, or a roller screw that converts the rotary motion into linear motion at the end of the actuator. Um, so some common terminologies that you would see with actuators are what is the maximum current, voltage, power. Whenever we have something with a lead screw or a pitch, then that's a common term that you're going to see. What is the lead of the actuator, pitch of the actuator, gearing ratio. Backlash is another thing that you would commonly see with electric actuators, especially with low end lead screw actuators. And resolution, again, what is the smallest movement that an actuator can produce? That's another term. Backdrive is a common terminology that you would see, especially if you're installing a waveguide that has to work against gravity. Um, and then types of actuators, you have inline and reverse parallel. Some actuators have limit switches or end stops. And then type of motor used in the actuator, you would commonly see servo, stepper, brushed or brushless DC motor. So actuators are providing the driving force to the guide structure so that it can position the web. In terms of thrust, the thrust is the amount of force that is exerted by the actuator to move the guide structure. And this thrust really depends upon, as we saw before, mass of the structure that we are trying to move, what is the friction there, how fast you want to move, and sometimes gravity as well, if you're acting against gravity. In terms of sizing actuators, these are some of the things that we would need to know to size an actuator properly. Web line speed, mainly because if you have a slow moving web, the maximum disturbance frequency that you can get really depends upon the speed of transport of the web. So if you're just moving at 100 feet per minute, you might not need a high dynamic response, while if you're moving at really high speed, you might need a much higher dynamic response. That's the main reason why we need that. And then the dynamic response is related to the acceleration. Acceleration is related to the thrust. So that's why line speed becomes important. Guide structure weight and roll weight. Again, if you're trying to move a big mass, we need to know that what type of bearing you're using, so that what is the breakaway force that we need to overcome based on the coefficient of friction of the bearing. And then what kind of disturbances we are trying to correct for. Again, like I said, there is a correlation between the amount of disturbance that can propagate through a roll-to-roll machine. That really depends upon the speed of the web. The faster you go, higher frequency disturbances can go through. So the web acts as like a low-pass filter. And then the acceleration. And then if you have to look at any gravitational effects. So these are some of the key factors that are involved in properly sizing an actuator. But like I said, actuators are pretty straightforward nowadays. Just need to have some basic questions answered, and then we'll be good to go. One of the most important parts of web guiding system is the sensor. It is important because what you can't measure, you can't control. So if you have a poor sensor and you're not able to measure the position properly, then there's no way that we can get the accuracy that we need. In terms of sensor terminologies, range, resolution, accuracy, linearity, those are some things that you would see. Type of sensors, infrared, optical, ultrasonic, air, type of things that you're trying to look for in terms of web position. Are you trying to look at edge of a web? Are you trying to look for a line on the web or a contrasting feature on the web? How fast can the sensor measure? Um, and then pass line and plane change, these are not important nowadays, but older ultrasonic sensors have issues with pass line changes, so you can't have the web too close to the ultrasonic emitter because it might reflect the sound waves in a way that doesn't provide an accurate measurement. And then temperature drift, again, ultrasonic sensors can have issues with temperature drift when we have the piezoelectric crystal frequency changes, and then what kind of a signal output that you get from the sensor. That's some of the terminologies. So essentially, range of a sensor is what is the maximum lateral displacement that the sensor can measure. Most often for web guiding applications, range is not that important just because of the fact that you're going to bring it in. But it does becomes critical when you have web width changes and things like that. So most often, range is like how much change in the lateral position that you can measure with the sensor. Resolution is the minimum lateral position change that the sensor can see. So if you want to guide a web to 5 thousandths of a inch, then you better have a sensor that can have 4x or 2x higher resolution than the guiding accuracy. Accuracy is basically an indication of how close the sensor measurement is to the real measurement. This becomes important for certain types of sensors that are affected by material properties like opacity, porosity, and things like that. So this is an important characteristic of a sensor. And then linearity is like how consistent is your measurement with respect to the actual position across the entire range of the sensor. That's what linearity means. So in terms of sensing, why is it important? Like I mentioned, some sensors have issues with material properties like opacity, porosity, or reflectivity, or they may be affected by environmental issues such as airflow, temperature changes, or vacuum, and things like that. So, uh, if we can't measure, we can't control. So that's why sensing is an important part of having a good guiding performance. Most often you would see these type of sensors uh, we refer to as opposing beam or fork style or horseshoe style. There are lots of different names for it. Basically how this works is you have one arm emitting a certain type of signal and the other arm receiving that signal, and then the web that goes in between it blocks it. It's a pretty simple technology, work sensing principle, and it works well for a lot of different cases. The problem happens whenever, uh, depending upon this type of sensor signal that you have, if the web allows that signal to leak through. Um, when it's blocked by the web, that's where the problem occurs. So we talked about linearity, resolution, range. All of those things are affected by this kind of sensor whenever that change occurs. Uh, this sensing signal can be air, it could be optical, like visible light or infrared light, or even UV light, and then it could also be sound like ultrasonic. It really doesn't matter. And then whether this material is opaque or porous to that signal is what it matters in terms of how well you can guide. And often manufacturers recommend different sensors for different materials and different conditions. So you will have a plethora of sensing technologies out there. Like I said, the main disadvantages is material dependent, gain change occurs, and then requires calibration if you want to get a really good guiding performance. There are other sensor technologies out there, like ours, which are not affected by material properties and some of the environmental conditions. I'm not going to go into detail about our sensor technology here, but just going to give you a quick overview. Basically a high accuracy, direct measurement or absolute measurement, and then our resolution does not depend upon the range, and it can work with any material. I'll give you some resources at the end of the presentation so that you can take a look at our stuff. So that's the sensor. So finally, the final component of the web guiding system is the controller. So the controller is basically the central processor that takes the sensor input, and then computes what the corrective action needs to be, and then it sends that information to the actuator. Um, Nowadays, the controllers also include a human machine interface, like an operator interface, but previously the controller could be standalone. It didn't really have an interface, and even the controller could be analog in the sense of electrical analog or pneumatic analog controllers. So basically, controller is taking the sensor signal and then um, making the necessary computation so that the actuator can be positioned at the desired location. In terms of terminology, gain is one of the most common things that you're going to hear in controllers. That's basically saying how quickly or what kind of a dynamic response that you need. That's basically the gain is going to do that. Other things that you're going to see is operating voltage, power consumption, whether you have a operator interface or not, and then whether this is a controller for a servo motor or stepper motor or whatever that is. They have drives or drivers for it. How many sensor inputs you have, does it have Ethernet connectivity? Does it have remote control and stuff like that? In terms of the control structure, most control systems have WebGuide control systems have this kind of a structure where you have a fixed gain proportional control. You really don't need anything more than a proportional control for a WebGuide because there is integrator built into it. But usually you have something like you have a motor, it might have a current loop, it might also have a velocity loop with a tachometer or something like that. And then you have a guide structure which has its own transmission ratio. And there's the web dynamics, which is unknown. Web dynamics means that if you move the guide 1 mm, how much is the web going to move? That really depends upon uh, transport conditions, the stiffness of the web, tension, and all those kind of things. And then finally, you have a sensor that measures the edge position, and then it sends that to a position controller that's going to drive all of these loops. So this is a pretty simple architecture for most WebGuide controllers. They are fixed gain, and most often they are detuned because of the stability and all the other reasons. Most WebGuides, their controller is kind of detuned for the conditions. Um, if you want to get the best out of it, you would need to retune them. And the tuning has to be based on the optimal performance because the web dynamics is unknown. Um, Most often, DC motors or DC servo motors or stepper motors are used in this kind of a control structure. It's pretty common. There are some other advanced control technologies, which are like adaptive control, where the controller can adapt or learn on the fly, and tuning may not be required. When we say learning on the fly, it means that maybe it adapts to sensor gain changes or the sensor, um, the dynamics of the web, and all those kind of things. It's possible that we can have a controller that can adapt. In our case, we have a pretty similar structure as the one I showed in the first one. It's still a fixed gain controller, but with some motion control aspects built into it in terms of S-curving the position and having trajectories for velocity. We can increase the stability of the controller and provide a pretty aggressive output performance. Again, pretty similar. You can have a current loop, a position loop, if you have a encoder, and then position of the actuator here, and then finally the web position, which includes the web dynamics. Just to give you an idea, we have a lot of different uh, things that we can do with the controller, but the dynamics is basically if you move this is showing a step response, open loop step response um, for a web. This was like a non-woven web that we had at different speeds, and see how it behaves. And you can see that when you have a step, even though it's open loop, it's trying to get there. And the dynamics, open loop dynamics, is different based on how fast you're running. So faster you're running, it gets to that desired location uh, as fast as possible. But the slower you're running, it takes longer to get to that desired location. Again, this is an open loop response. This is the final part of the whole web guiding thing, which is the dynamics of the web. Now, if we add a controller to it, and this was our controller, then we can have a much better response, and we can actually push the web guide. In this case, at the two different speeds that we were running at, this was the reference change, and this was the actual response of the web guide at the sensor. And then when we have another sensor installed, one span downstream, you can see how long it takes for that to go through. Um, Again, when we have a step response, we were able to get up to about 170 millimeters per second, or like 7 inches per second. This is about close to 70% improvement over an open loop response. And again, this is closed loop. That means you are actually actively guiding the web. So with a proper control structure design, you can get like a high bandwidth system close to 6 hertz or something like that. And then even get a well damped system. So you can actually have an aggressive correction if you need to. Um, in terms of the characteristics of a good web guiding system, is that it should have the ability to attenuate disturbances, easy to tune. Obviously, it needs to be stable, has good processing power, so that it can process multiple sensors, have industrial Ethernet connectivity. These are for advanced functionalities, and then smarts and intelligence for Industry 4.0. So the final question here is that, well, you have a web guide, and we talked about all these different things. What is the accuracy, or how accurately can you guide a web? Um, it actually depends. Like I mentioned, there are lots of different parameters there that are going to affect the accuracy of the web guide. Uh, if you are just dealing with a steady state error, uh, we can expect plus or minus 0.25 millimeters. If you have a good machine and a perfect material, this is what you can expect. And higher accuracies are possible, like in printed electronics and stuff like that. You can get much higher accuracy. But again, if we're dealing with steady state errors, you have a good edge and all those kind of things, this is possible. But the problem is that most web guides are going to come into transient errors. These are either disturbances or materials, or material properties that are going to affect the disturbance of the web guide. Now, if you're trying to correct a transient error, it really depends upon what is the magnitude of the error, what is the frequency of the error, and so on and so forth. And another important thing that we need to consider is that these transient errors can actually propagate downstream of the sensor, and these are called what are called as weave generation. Even though you correct it at the sensor, you don't really know the angle at which the web is approaching, and that can cause what is called as weaves downstream. Again, if you won't have good guiding performance if you have wrinkles. I mean, if the web is wrinkling, that is going to cause the edge to move back and forth, and there's no way that you can have good guiding performance with that. Or edge curl or flutter, or sometimes plane change can also have that effect. If you have large magnitude error and your stroke of the actuator is limited, or the correction that the web guide can provide is limited, then you can expect good guiding performance whenever the actuator tops out on either side of its stroke. Um, Again, if you use a lower bandwidth actuator and you have a higher frequency error, you can expect good guiding performances. And sensor, if you don't have a good sensor or if it has gain changes, then you can expect good guiding performance. And then improper installation can actually amplify the error. So that's another thing that we can expect. Anyway, so just to summarize the factors affecting, we talked about it: machine related, process related, material related, and the web guide related, which is like the stroke, deadband, actuator backlash, correction, stroke limit, and things like that. So in terms of design requirement, a good knowledge of the conditions like web speed, location, thickness, stiffness, environment, tension, desired correction, all of these are important for us to have a good, well-designed web guide. And then obviously, if you have a good understanding of all of these, we will do well. I know we're running out of time. This is my last slide, and I just wanted to bring this up to summarize it. Um, just to summarize our fundamentals of web guiding, well, webs, machines, process, nothing is going to be perfect. So we need web guides to correct for it. Most of the web guiding, um, or the traction or the steering of the web, happens because of the normal entry rule. So whenever you have a misaligned roller or an out of round roller, all of those things are going to affect the disturbance created within the machine. The sensors, when you're installing it on a web guide, we need to be installed as close as possible to the web guide. And then the web guide has to be located as close to the process that needs alignment. We cannot have an unwind and have a guide on the unwind and then have 10 spans later you have a process where you need the alignment. We need to have the web guide right next to the process where the alignment is needed. None of these action of the web guide will have any effect if we don't have traction. Traction is indirectly related to tension. So if you don't have good tension or traction between the web and the roller, you cannot expect good guiding performance. Um, Proper installation, depending upon the type of web guide we have, is important. And then also, improper installation can actually adversely affect your material. It may wrinkle the material, create edge stresses or instability. And finally, the overall guiding performance, it's actually a function of the sensor, the actuator, the controller, even the web itself. So in order to have all of those, we need to have a pretty good, um, all of these have to be pretty good. Um, that's the summary, and I do have a slide which shows some additional informations on different things that we have on our website. I will leave this for a quick second. And I was supposed to have some polls that I was supposed to share with you, but I didn't. So I'm going to have some of these put up right now. And if you can answer these questions, that would be great. Um, Basically, we want to make sure that uh, this webinar, whether it was useful to you or not, and also know um, what would be something that you would be interested in the future. Uh, and what are some of the biggest problems that you see in your operation? Is it web guiding? Is it tension related? Is it raw material related? Or process quality issues? Okay, so while I have these polls on, let's see if I have anything that I have missed in the Q&A. Okay, so there was a question about why would you want a deliberately oscillated roll? Well, there are some times where um, you have gauge band variation. That means the thickness of the web across the width of the web is different. This is especially true when you're folding the web or like in shrink sleeve applications. And if you guide the web at the same location, the gauge band variation is going to have different stresses on the wound roll. So the hardness of the roll along the width of the web would be different, and that causes problems in terms of telescoping, and when you transport the rolls and things like that, it might have some issues. So what they do is they deliberately move the web guide back and forth, so that the the thickness variation is evenly spread across the entire width of the roll. So that's why you want to deliberately oscillate the roll back and forth. These are only when your converting process has an intended thickness difference, like when you are sealing or closing and sealing a web guide. Um, there's a question about master slave application. What is that, and could you give an example? Okay, so whenever you have a lamination process, you have one layer of the web that you need to laminate with respect to another layer of the web. That's when it would be important to have master slave. So one layer of the web can be guided to a location, and then the other layer of the web, its reference or the guide point would be dynamically adjusted so that you can match those two webs together. It can also be done if both these web guides are um, guided to the same machine reference. But usually that's a problem because when you're moving the sensor, you don't know if you put them exactly at the same machine reference. So in that case, you would have one web as a master, and then the slave web guide will have its guide point changed based on the master position. Okay, so let's see. Um, got another poll here. Uh, what are your biggest challenges with web guides? Is it the lack of performance? Is it the complexity of setting them up? Or doesn't have enough features? What is the biggest challenge for that for you? And finally, um, in terms of future topics, what would be of interest in the future webinars? We talked about fundamentals of web guiding here. We didn't talk about anything related to web guiding applications like edge guiding, center guiding, line guiding, contrast guiding. Those things we didn't talk about. There are advanced web guiding concepts as well. Are you interested in measurement and sensing technology or general web handling topics? And would you be interested in training on roll to roll products? Okay, so there is a question from Jay, and let's see if I can allow Jay to talk. Oops, that went away. Okay, there we go. Okay, Jay, I think your microphone should be enabled. Jay, did you have a question? Okay. Um, well, um, hopefully, um, we were able to give you a little bit about the fundamentals of web guiding. And let's see if we can show some of the results here. Oh, anyway, um, thank you so much for your time this afternoon, and thank you giving us an opportunity to talk a little bit about web guiding and web guiding fundamentals. I have put our contact information there. If you have any other further questions, please let us know either by email or calling us. Then we have this webinar recorded, and what we could do is we will share the video of the webinar in a follow-up email. And if nobody else has any other questions, we would stop the session and appreciate your time. Thank you, everyone. Have a good day.